Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 5.17. Problem statement says, spray drying is a process in which a liquid containing dissolved or suspended solids is injected into a chamber through a spray nozzle or centrifugal disc atomizer. The resulting mist is contacted with hot air, which evaporates most or all of the liquid, leaving the dried solids to fall to the conveyor belt at the bottom of the chamber. Powdered milk is processed. Powdered milk is produced in a spray dryer 6 meters in diameter by 6 meters high. Air enters at 167 degrees Celsius and minus 40 centimeters of water pressure. The milk fed to the atomizer contains 70% water by mass, all of which evaporates. The outlet gas contains 12% mole water and leaves the chamber at 83 degrees Celsius and 1 atmosphere absolute pressure at a rate of 311 meters cubed per minute. Part A, calculate the production rate of dried milk and the volumetric flow rate of the inlet air. Estimate the upward velocity of air in meters per second at the bottom of the dryer. First things first, draw a picture. Okay, so we've got stream 1, milk coming in down here, spraying out and kind of falling down, and then we have dry air flowing up. Stream 2, it's at these conditions. This is a gauge pressure that they gave to us, and it's in a weird unit, so we'll have to convert that. Okay, then we've got our wet air coming out the top. The wet air, we know its volumetric flow rate, we know its temperature and pressure, so that gives us quite a bit of information. We also know the mole fraction of water, which is really nice. Okay, the diameter and height of this chamber, we know that the height of the chamber is 6 meters and the inner diameter of the chamber is 6 meters as well. Okay, this is our conveyor belt. All of our solids fall onto that and flow out this way. So all the solid milk comes out. That's 30% of stream 1 by mass. Okay, so let's do our materials balance. We have 3 components. There's no chemical reactions going on, so moles are conserved, mass is conserved, and we're just keeping track of just these components. We don't have to do molecular balances in this case necessarily. Okay, so we've got water, air, and then we have solid milk. Solids, whatever that is. Okay. Water, we have water going in. That comes in stream 1. M1, I have all the unknowns highlighted in red. Okay, stream 1 comes in and all the water goes out in stream 3. For the solids, all the solids come in stream 1, they all go out in stream 4. All the air comes in stream 2, and we're doing this one in moles, it's a little easier to do in moles, and all the air goes out in stream 3. Okay, we have quite a few unknowns. The only few ones that, we do know. Oh no, we don't know how much air is. Well, we kind of know how much air is going out in stream 3, but here, let's look at our process specs. Okay, so process specs, we know that there's a certain weight percent of water in stream 1, and the rest is solids, so the solids is 30%. And we know the mole percent of water going out in stream 3, so we know that the air percent is this much. So these ones we can figure out. Okay, so this is our equation of state. This is our equation of state model. We're going to use the ideal gas law. Okay, so ideal gas law is pressure. Okay, so our ideal gas law is pressure times volume equals the number of moles times R times T, temperature. Okay, we're solving for molar flow rate because we want to know it for this guy right here. Okay, so we solve for the molar flow rate. We put all of our specs that they gave to us in the right units, right? So we have this one in pascals, we have this one in Kelvin, and we have this one in meters cubed. Okay, so then we go ahead and solve for that. That's our molar flow rate. Now that we know the molar flow rate here, and we know what the air is from that equation, now we can solve for what N2 is. Okay, so we know what N2 is, just based off of that. That's nice. Then, now that we know what N2 is, we're splitting it up into water, nitrogen, and oxygen. And we're going to use this equation in order to calculate what the water balance is. So we're going to be trying to figure out more out about this equation. So you'll notice that N2 is in moles. This stream is in mass. All right, so we're going to have to do a little bit of molar mass equations here. That's what all this is for. Okay, we write down our mass balance here from what we did for water. Then we kind of combine this term into one single term, and we know that it equals, we know that this number also equals the molar mass times the molar flow rate of water. So now that we know that, we also know that the molar flow rate of water is equal to the number of moles times the mole fraction. Okay, so we're just kind of converting everything into mole fraction. So given all of these true statements, now we can say M1, which is what we want to calculate for, is equal to the this guy, which is our total mass of water flowing, divided by the mass fraction of water in that stream. And we know that the total amount of water flowing is equal to the molar mass times the molar flow rate of water. And then we can convert this molar flow rate of water into, well, it's the molar flow rate times the mole fraction of water. Okay, and all of these things we know because we've solved for them previously. So now all of these things are known. We can calculate what M1 is. Okay, so M1, plug in all of our numbers, and we get a molar flow rate of total molar flow rate of stream 1. Okay, M4, this is our solids balance. So M1 times the amount of solids percent. We already know that that's 30%. Okay, so that's the total production rate is M4. So that's how much we have solids, powdered milk, leaving. Okay, we already solved for N2. Well, we didn't actually solve for it, but we kind of pointed out that we had basically solved for it by knowing what this is. Okay, so that's N2. We're going to use that a little bit later, so I'm just going to say N2 is this, so I don't have to keep writing the number over and over. Okay, so if we know what N2 is, then we can solve for what the volumetric flow rate is, because remember they asked us for what the upward velocity of the air is. Okay, so we're going to figure out what the volumetric flow rate is, and then we're going to divide that by the cross-sectional area of the pipe in order to figure out what the velocity of the air is instead of the volumetric flow rate. Okay, so we use our gauge pressure, right? This is P2, but they said, you know, it's atmospheric pressure plus it's at a slightly negative pressure, right? So we have to convert our inches of water into pascals and then add it to the pascals over here. We get a little bit less than atmospheric pressure in pascals there. So now we've solved for our number of moles. We know what R is, temperature, pressure. So now we can solve for the volumetric flow rate. There you go. That's the volumetric flow rate. The velocity of the air is equal to, and it changes obviously because the pressure and temperature conditions are changing as the air flows through and picks up all this water, right? So They specifically said at the bottom of the dryer, not at the top of the dryer. So once you get to the top of the dryer, the flow rate's going to be different than when you're at the bottom of the dryer. Okay? So at the bottom of the dryer, what is the velocity? It is the volumetric flow rate that we just solved for divided by the cross-sectional area of the pipe. Okay? Cross-sectional area is equal to pi r squared because it is a circular silo pipe thingy. Okay, so pi divided by pi times r squared equal to this, so that's our cross-sectional area. So then that means our volumetric flow rate, or our velocity, is this right here. And that's the answer to part A. And it said, well, what's the problem? What problem would you guess would occur if the velocity is too high? Okay, so we look at our object falling. This is a lesson in terminal velocity. Okay, so we've got our object here. Our object right here is falling at a certain rate. It's falling in air. Okay, and the air, we're going to assume that the air is stationary. Okay, but it all depends on your frame of reference. Maybe the object is stationary and the air is flowing by. It just depends on your frame of reference. So let's say in our case the object is stationary, not moving at all, and the air is flowing by instead of the object. Okay, that would mean that the forces on the object are completely imbalanced. There's no force, because if there was a force, then the object would be speeding up or accelerating. Okay, so we're saying that the object is stationary, it's not moving with respect to the air. That means there's no forces acting on it. That means that the force of resistance, the air resistance, is equal to the force of the gravity pulling it down, or opposite, equal and opposite. Okay, so that means these two forces completely balance each other out. They're equal to each other. That means the net force is zero, no acceleration, velocity is constant at zero, or constant depending on your frame of reference. It's equal and opposite to how fast the air is flowing around it. Well, what would happen if the object is not at equilibrium? What if this air resistance is actually bigger, right? Okay, what if air resistance is bigger? Okay, bigger force on this object is no longer being pulled down as quickly. That would mean that there's a greater force pushing this object up. Okay, so the object is not falling anymore, even though there's a gravitational force pulling it down. This force is so big, now the object is actually going up. There's lift. The object is flying, right? Okay, so object does not fall. Let's go back and look at our picture. Uh-oh, what happens if the object doesn't fall? Okay, it gets sprayed down here, and then whoop, solids go out the wet air. Okay, so instead of falling onto our conveyor belt, they come out with our air, and we start blowing milk out the top. Okay, so that's not what we want, right? Okay. Well, that is it for problem number 5.17. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.